Hi, my name is Caitlin, and today I will be using balloons to represent molecular geometries and the number of bonding and lone pairs in each. I will show the number of bonding pairs and lone pairs and how that affects the shape of a molecule according to the VSEPR model. This stands for the valence shell electron pairing repulsion theory. In this lab, it is important to remember that a balloon represents an electron domain, which is going to be the area of electron density around the central atom. I will be using blue balloons today to represent bonding pairs or bonding atoms, and I will be using red balloons to represent non-binding pairs, also known as lone pairs. All right, so the first example I have is linear. An example of one that looks like this would be carbon dioxide. This has two bonding areas, which are represented by the two blue balloons, and no lone pairs, since I have no red balloons on here. Notice how these bonding areas are attached to the central atom, which would be right here in the middle. These atoms spread out in a straight line, and they have a bond angle of 180 degrees, and both the electron geometry and the molecular geometry are linear. This next example I have is trigonal planar, which can also be an example of boron trifluoride. It has three bonding pairs or electron pairs and no lone pairs, again, because there's no red balloons. It can form a flat triangle shape around the central atom. The bond angles are about 120 degrees for this geometry, and the electron geometry and molecular geometry are both trigonal planar. Hi, the third example I have is called a tetrahedral, like methane. It has four bonding pairs. Pretend the black one is a blue one because I ran out of blue balloons. The bonds are evenly spaced in this 3D-like pyramid shape, which creates angles of about 109 degrees. And both the electron and molecular geometry are tetrahedral. The next example is trigonal pyramidal, like ammonia. It has three bonding pairs, represented by the blue balloons at the bottom, and one lone pair represented by the red balloon on the top. This lone pair pushes down on the bond slightly, so it gives it this like pyramid-like shape. The electron geometry is tetrahedral, but the molecular geometry is trigonal pyramidal. The bond angles, are slightly less than 109 degrees. Okay, this next example is bent, like water or H2O. There are two lone or non-binding pairs at the top and two bonding pairs at the bottom. The lone pairs are going to repel the bonds, so they're going to push closer together. That's why I have them close to show this separation right here. And then this angle for these bonds are about 104 degrees, and the electron geometry is tetrahedral, while the molecular geometry is bent. The next example is trigonal bipyramidal, and an example of this is phosphorus pentachloride. It has five bonding pairs. Remember, pretend these are blue. It has five bonding pairs and no lone pairs. Three atoms form a triangle on the plane, and then one is above, and one is below the central atom. The bond angles are 120 degrees in the planes and 90 degrees between the top and bottom. Both the electron and molecular geometry of this are trigonal bipyramidal. This next shape was a little harder to make, but it is called seesaw. An example is sulfur tetrafluoride. It has four bonding pairs and one lone pair. The lone pair takes up some extra space, which makes the symmetry off a little bit, and the bond angles slightly less than 120 degrees and then 90 degrees. The electron geometry is trigonal bipyramidal, and the molecular geometry is a seesaw. T-shaped comes next. An example of this is chlorine trifluoride. It has three bonding pairs and two lone pairs. The lone pairs occupy this space around the middle, which leaves the three atoms kind of to form a three shape between the bonding atoms. Um, the bond angles are slightly less than 90 degrees, and the electron geometry is trigonal bipyramidal, and the molecular geometry is T shaped. Next comes octahedral, like sulfur hexafluoride. There are six bonding pairs. Remember, these black ones represent the bonding pairs with the blue ones. And there are no lone pairs. The atoms are arranged evenly around the center, so they have 90-degree angles between the bonds. And both the electron and molecular geometry are going to be octahedral. All right, the next one is square pyramidal, like bromine pentafluoride. It has five bonding pairs, one, two, three, four, five, and then it has one lone pair which sits at the top. Since this does sit at the top, it slightly like shifts the and like tilts the base atoms downwards. So the electron geometry is going to be an octahedral, and the molecular geometry is going to be that square pyramidal shape. Okay, and the last model of this presentation is square planar, like xenon tetrafluoride. This is going to have four bonding pairs, four right here, and then it's going to have two non-binding or lone pairs. Those are going to sit opposite of each other, and since they sit opposite of each other and they're pushing away from other atoms, it's going to push all of the bonding pairs into like this square shape. The bond angles are 90 degrees for all of these, and the electron geometry is octahedral, while the molecular geometry is square planar. Okay, so as you can see, the shape of a molecule depends on the bonding pairs and lone pairs that are present around the central atom. Lone pairs tend to push the bonds away, which will change the molecular geometry, even when the electron geometry stays the same. Thank you so much for taking the time to watch my presentation.